All right, so I was just showing before the record, I forgot to record, but before the recording, I was just showing parafilm, which is just a handy wax film that we can use to cover beakers, glass, and burettes, like I did up here. And it stretches, so a piece of parafilm like this can fit over a 400 milliliter beaker like this. It's pretty thin, but it's pretty thick here. So, all right, this is my waste beaker here. And so what we're going to do is we're going to continue. So I left this pretty much sitting here. That's the one advantage of the lockdown. Nobody's using this lab except for me. And so what I'm going to do is I'm going to dump out, there's some sodium, actually this is the acid. There's some acid in the burette here, so I'm going to dump that out. I already dumped out the waste earlier. We'll take off the parafilm. Parafilm is just one-time use, and then you just throw it away. I'm throwing that away. It's not flowing because I have parafilm at the top. I'm going to remove the parafilm at the top here. So we'll throw that away too in the garbage. Okay, now it's flowing. So I'm just going to purge out the tip here. And the same thing with the base. The base burette has, this burette is not good because if you take a look, what happened over the weekend was, if you see the lab bench here, there's some evidence of spill. And then if you look at the tip of the burette, there's a drop hanging there. That's telling me that this is leaking. So this is also could lead to poor precision if we got leaks like this. And this is already very tight. And so the leak is some other kind of problem because the stopcock is extremely tight right now. And so this is not a good burette because of that leakage. Well, I'll try to tighten it some more. Tightening it along with this nut here. If you get it too tight, it's hard to turn this. So I'm going to get it as tight as I can without making it too hard to turn. And if it's too hard to turn, you can't get that as precise of a movement as you might like. A little bit of drop hanging there. Wow. Oh, okay, let's see. Forgot the parafilm at the top of this too. Take the parafilm off. Let's see if it's flowing. It's flowing right. So I tightened that. All right, so now I'm just going to refill the burettes. Refill it use the funnels here too. I'm going to actually let me do this. Let me show you this. Yeah. All right, I have my waste beaker here, so I'm just going to rinse off the funnel. You know, there's two ways. When we rinse off this type of glassware, we rinse off with DI water like this. And then we give a final rinse with the solution that we're pouring because there are little droplets there. It's too hard to dry this. And so the final rinse will be just of the solution. Actually, I have a transfer beaker too, but if I'm going to use a funnel, I probably don't need a transfer beaker. Okay, so this is the 1049. So this is the sodium hydroxide. I spilled some sodium hydroxide. Sodium hydroxide is slippery to your fingers, so you can tell if you spilled some on your fingers because they'll become very slippery. And then I'm going to pour the sodium hydroxide into the burette here. Again, when we're using a funnel like this, you know, I like to transfer with a beaker because a beaker has a spout, and it's easier to pour. I find it easier to pour from beaker than a Florence flask like this into a funnel, because I get less spillage. But if you use a funnel, you have to hold the funnel up here. Otherwise, it creates a tight seal on the beer. We don't want a tight seal. We want air to get in there. Fill it. All right. Leave the funnel here. Okay, it looks like I poured a little bit too much there, so I'm over the 0 mark. So I'm going to just let a little bit drain here. There. I got to make sure I have no air bubbles. That looks good. All right. Then let's go ahead and fill the acid. Let's set this aside. Okay, same thing here with the acid funnel. I'm going to rinse with DI water here. And then this is called the final rinse. I'm going to give it a final rinse. So I just rinsed with DI water. I'm going to get a final rinse with the solution that I'm pouring through the funnel to avoid contamination. You know, water, you don't think water will contaminate it, but this solution, we're interested in the concentration of the solution. So concentration of the solution will change if there's additional water in the solution dilution. Let me go ahead and fill this. I'll lift up the funnel and then fill this. All right, I'll leave the funnel in there. Okay, this one I also filled past the mark, so I'm going to drain a little bit here. Then we'll take some measurements, readings here. Okay, when you do this in lab, what you want to do is you want to get the meniscus eye level to avoid parallax. So we get it eye level, and then I can have the meniscus reader here to do that. And so I'll take a shot of this. Yeah, let's see. Make sure this is a little bit tricky, as I mentioned before, because the phone, the lens, see, I'm just going to guess it's about the right level. Because the reading can vary pretty dramatically. If you're reading it from down here versus reading it from up here, you know, it could vary a couple of tenths, you know, or even 3/10 of a milliliter, which is quite a lot. And that's going to create bad precision. But let's take a look at that reading there. And then see. Share. Move this over here. I can't see the camera right now. So you can't see anything, can you? Hey, can you guys tell me what that is? Let me try to blow this up here. Just 1 minute. Okay, there we go. Okay, can you guys tell me what the reading is? Can you guys see the reading? 0.35. Francis, let's take a look. Yeah, that looks good. 0.35. We can go with that. And so we'll record that in the notebook here. This will be run. Actually, did we calculate the molarity from run 5? No, I don't think I did. So this is actually run 6. And we'll go with 0.35. I want to see if this leaks a little bit on this one, but I didn't calculate the last molarity. So let me calculate the last molarity, run 5's molarity here. I guess we ran out of time. And so taking a look at run 5, the volume of sodium hydroxide that was used is 20.82 milliliters, just this minus that. And the volume of HCl that was used is this minus that. And so it's going to be 20.46 milliliters. Okay, and then we'll calculate the molarity of the sodium hydroxide. The molarity of the sodium hydroxide, again, it's just going to, well, I'll just rewrite it down here since it was last week. Molarity of the sodium hydroxide is going to equal the liters of HCl. This is the stoichiometry that we're going to use. Liters of HCl is, we'll just move the decimal 3 over, 0.02046 liters. So 0.02046 liters. This will be the HCl solution. And then we know the molarity of that HCl because it's the HCl standard. It was 0.1032 moles of HCl pure per liter of HCl solution. And then we're going to convert that into moles of sodium hydroxide. It's a 1-to-1 mole ratio based on the chemical equation. 1 mole of sodium hydroxide for every, let me get rid of that, for every 1 mole of HCl. Here. Okay. All right, that's going to give us moles of sodium hydroxide, and then we just need to divide it by the liters of sodium hydroxide. So how many liters of sodium hydroxide did we use? Well, I'll just move it 3 over. So it's going to come out to 0.02082 liters of sodium hydroxide. And so 0.02080 liters of sodium hydroxide solution. Okay, and then do the calculation here. So I have 0.02046 times 0.1032 divided by 0.0208. So that gives us 0.10151 molar sodium hydroxide. And so what we'll have to do is we're going to have to calculate the percent difference. So far our best runs are run 4 and run 3, 3, 4. And so how does this run stack up between run 3 and run 4? And so let's look at the numbers here. Looking at the numbers, run 3 had a 1034.4. Run 4 had a 1035.1. And so what we're going to do is we're going to compare it to runs 3 and 4. And so what we'll do is we'll pick the biggest out of all 3. And so the 3, 4, and 5 looks like run 4 had the biggest number, 1035. And so this is going to be the percent difference for runs 3, 4, and 5. And so we'll pick the biggest, which is run 4, which is a 1035, 1, minus the smallest. Now the smallest is going to be run 5 at 1015, 1. So this is going to be 0.1015 sub 1 divided by the smallest, 0.1015 sub 1 times 100%. And so let's see what that comes out to here. And so I'll just leave, I'm going to leave all the digits in my calculator. Minus 1035, 1, divided by 1015, 1, times 100. Oops, I forgot to hit equals. No wonder it's 91.8. All right, I have to hit equals for the numerator. Equals 1035, 1, minus 1015, 1, equals divided by 1015, 1. Oops. I got to get my calculator. 1015, 1 times 100. Okay, so this one didn't work out so well because this one is a 1.97% difference. And so it's too far off. The precision's bad. Either I'm not reading it consistently or this, well, the leak is very slow. So it is leaking a little bit. It's very slow. I can see there's a drop building right there. Up here, right. Well, 1.97% difference. Oops. So let's do another run and see how it goes. And so run 6, I'll just do it on the next page. We do as many runs as it takes. Now, the risk is running out of sodium hydroxide or HCl, since you might have a limited amount. So we'll have some sodium hydroxide, HCl. The initial volume is 0.35 milliliters. Okay, let's check the initial volume for the HCl. So same thing here. I want to make sure my eye level is perpendicular to the meniscus here. In other words, I'm going to try to make sure the camera level is perpendicular to the meniscus here. Get it? Blow out. Zoom it in. Make it easier to see. Okay, let's see how this goes here. All right, so what do you read this one as? Move this window a little bit, just 1 second.
Oh God, he texted me yesterday.
Okay. Need to get this over. Oh, I see. There we go. So 191. Okay. Let's see. Yeah, 191 or maybe a 192. I would, you know, because what you have to do here, let me see if I could just freeze that. Right. Let me see if I can write on this. Oh, I can't. Let me try that one more time. I wonder if I can write on the screen here. I guess not. Okay, the reason I'm thinking it's a more of a 192 is this is the way I would look at it. Okay, I would cut the, okay, take the center of this line and the center of this line and then go in the middle. And so the middle is going to be a 195. Okay, and then go from the center of this line to the middle, and you should have 5 increments, you know, starting off with 0 right in the center, and then 1, and then 2, 3, 4, 5. So you should have 5 increments. And so if that were a 1, then you're going to have a lot more. That might even be a 2, you know, depending on, just imagine the center of this as being 5, 0. I mean, not 5, 9, 5. And so we have 90, 91, 92, 93, 94, 95. So that's why I'm thinking it's a 92 rather than a 91. 91 I would have had closer, you know, to the line here. And so I'm just, we'll just go with, let's just go with 92 for that milliliters here. Okay, now we're ready to go with our titration. So I'm going to get a flask. I didn't clean these flasks. I'm assuming that the last person cleaned it, but you know that might be a stretch. So what I'm going to do is I'm just going to give this a rinse. You know. Now I told you here. So I'll give it a rinse off. If this wasn't clean, I clean it with warm soapy water, you know, and then give it a rinse off with tap. Maybe I'll do that with the next one if we have to go for another round. If we have to go for another round, I'm going to be a little bit more careful, but I'll just show you what I mean. And so if I'm going to clean this with a little bit of soap, you know, we have soap here in the lab. I'll just do it over here. So those are probably in the way. Put a little soap in there, and then come over to the sink. Fill it, and then we have these. These are bottle brushes. And so we'll just use a bottle brush to clean the inside surface of this. And really, you can't trust the people who last use your glass equipment. So you can't assume that they cleaned it properly. They might have just got it good enough. You know? And so it's probably a good idea to clean your glassware before the experiment. Since I was using the instructor drawer equipment, I was thinking that I wouldn't have to do that. The last person should have cleaned it pretty well. All right, the initial rinse is with tap water. So rinse it with tap water. Get rid of all the soap, residual soap. Okay, and then we'll rinse it with DI water. DI water here. DI water is expensive, so that's why we just give the final or the second to the final rinse with DI water. I'm just washing out the tap water out of this, basically. The tap water was to wash out the soap. DI water is to wash out the tap water. And then we can dry it. I don't have to dry the inside of this because actually I don't have to dry this at all, really. The reason is because of this. We're measuring precise amounts of the solutions here, you know, the acid solution, the base solution here. And so we want to know how much, you know, exactly we used of this. And that's going to tell us how many moles of acid we have in there and how many moles of base we have in there. But if I have water in here, it's not going to change the amount of acid I add in there, and it's not going to change the amount of base I add in there. But I don't want to add water into this burette. If I add water into this burette, that would be a disaster because that would change the concentration of my solutions. And the HCl is a standard solution with a 0.1032 molar concentration. And so I don't want to change that. Otherwise, I don't know how many moles I added in there. And so that's why we had to do all the extra rinses for the burette solutions, because we didn't want to contaminate this what we call the standard solution with water. But here, this isn't, you know, this is going to change. Okay. See if we can get it focused here. All right, so this isn't going to change the amount of acid I'm going to use or the amount of base. I think this one's leaking too. A little bit. Let me tighten this stopcock here. All right, so let's do another run here. And so I'm going to add about 20 milliliters. And to prevent splattering, I'm going to lower this. So there's a drop hanging there. So there's a slight leak, looks like, in this burette too. So let me tighten that. So add about 20 milliliters. So I started at about 2. So I'm going to go to about 22. So that's going to be there. And so I have about 20 milliliters of acid in there. And then I'm going to add 2 drops of phenolphthalein, which is the indicator here. So 1, 2 drops of phenolphthalein. And then let's get rid of this burette. And we're going to switch over to this burette here. All right, and let's see the data from the previous runs. It looks like I used a little bit more sodium hydroxide. No, a little bit less sodium hydroxide in the run. So I'm going to stop before 22. And so I'm about 0.35, we said, 0.4. And so I'm going to go to about 20 milliliters, probably right before 20 milliliters, I'll stop. Let's see. Okay, I stopped at about 19.5 milliliters, and you can see there's a pink color there already. And so let's see if that pink color persists. So what I'm going to do is I'm going to take this out and then swirl it. Let's see. Well, the pink color didn't persist. And there's a lot of splattering on the inside of the flask, you can see. And so what I want to do is I want to make sure that I get all the solution mixed in there.
Huh? Yeah. I'm fine.
Okay. Now, if this are Chem 1A style titration, we have to be very careful because we can't overshoot it. If we overshoot it, then we'll have to trash that run and start over again. And so in this case, I'm going to do it like a Chem 1A style titration. And so I'm about, within a half milliliter range. A half milliliter is like 10 drops. A full milliliter is about 20 drops. And so I'm going to go just drop by drop. And so if I go drop by drop, I'll get it at least to within 1 drop. Probably, okay, so that was 1 drop. So maybe by the 8th drop, I might go half a drop. Depends on the color here, persists. The problem with this is if you're way off, you're going to be doing this for a long time. But a long time is all relative because starting over again, trashing that run and starting over again is an even longer time. And so it could be worth it. It depends on how many milliliters you're off by. Let's say you're off by 4 milliliters and you're doing it drop by drop. That's 4 times 20 is 80 drops. And so, oops. Yeah, unfortunately, this stopcock was too tight. And so that's what I was afraid of. I'd have too much in there. But it looks like I was off a bit. So now I'm going to really slow it down. Let me loosen this because it's too tight. Okay, so that was a drop, and got no color there. Let's see about this next drop. Still, maybe we got some color there. Let's see. Hard to see against the black background. But if I put a white background, you'd probably have a harder time to see it. We'll just leave it. Okay, there it goes. So we have a color there. Let's see if the color persists, and let's make sure I get all the splattering off the wall of the Erlenmeyer. The color didn't persist, so I think I'm within, a drop, maybe half a drop. And so this, in this instance, I'm just going to go half a drop. So I'll suspend a drop, a half a drop won't fall. And then I'm going to just use a little bit of water to spray it in here. So that was a half a drop. There's a very slight color to this, but it's probably not going to persist. And so I'm going to do another half a drop here. Okay, so that's a half a drop suspended, and drop it in. Okay, now I do see a very slight color. I don't know if you guys can see it also, but there's a slight pink color to this. It's extremely faint. It's hard to see, pretty hard to see, but maybe you can see it. It's so faint, I have my doubts it's going to last for 30 seconds. But so far, it's still there. But it's pretty much gone, I think. So let's go with another half a drop. Yeah. So suspend that. Wash that in. Okay, again, I see a very faint pink color. Let's see if it lasts. It's not persisting, so let's go with another half a drop. Spray that in. Okay, I see some color there again. See if this helps. It's probably harder to see for you guys. It's easier for me to see because I can see the slight pink color, but from your angle, it might be pretty hard to see. Move this. That's extremely faint. Could be my imagination too, but I don't know if you guys can see that. Extremely faint. Well, let's go with another half a drop since it's so faint, it's hard to detect. And so I'm going to just suspend a half a drop on there. Maybe a bigger half drop. Maybe this is about a 3/4 drop suspended on there. And let's wash that in. Okay, and then take a look at the color. Do you see that pink? Maybe from this angle you can see it better. All right, we'll just go with this. Let's see if this persists for 30 seconds or not. I'm going to set the stopwatch on. Okay, this persisted for 30 seconds. The color's there, but I wasn't swirling it because I'm holding the camera with one hand. So let me just swirl this and make sure. And also, let me make sure there's no splattering that's going to make this go back to colorless. There. And so the color hasn't faded. It's faded a little bit. You know, it's not as strong as it was at the beginning, but you know, the color is going to fade after a few minutes. The reason the color, I can make the color fade quite rapidly by exhaling on this. You know, you can still see that there's a little bit of pink in there, but let me exhale into this. By exhaling into this, I'm increasing the CO2 inside the flask. If I increase the CO2, CO2 is an acid. And so CO2 is going to make the color fade faster. And so now take a look at the color. The colors disappear. You see that? And so if the color, you know, doesn't persist after a few minutes, that's okay because there's CO2 naturally in air, and that CO2 is an acid. The CO2 gets absorbed into the liquid. Henry's law, remember, CO2. And so it persisted for 30 seconds. That's all we need. And so this would be a Chem 1A style because what happens is if you overshoot in Chem 1A, again, you have to start over because you only have one burette and you can't go backwards. And so let me, let's take a reading of the base burette right now. Okay, so I need to raise the burette because I need to get it eye level here, or I need to squat down a little bit to see it. And then let me try to get the camera. This is probably one of the reasons precision's tough, because I haven't been consistent with where I hold the camera. You know, I was holding it up here initially, and but the camera's at the top here, and so I'm definitely getting parallax, because I saw it based on, you know, being able to see the front and the back of the line. So let's try this. Okay, it's hard. The top line here is 20. And so this is going to be 20.1, 20.2, 20.3. So what would you call that? Let's see if I can blow that up. Oops. So everybody should take a reading. What do you guys call that? Okay, it's actually 20.30. Okay, that sounds right. It looks like it's right on the line. So that's what we're going to go with. We're going to go with a 20.30 for that. That's the base burette. So let me record that in the lab notebook, 20.30 milliliters. Okay, let's take the acid reading. So again, the same thing. I'm going to raise this up a little bit so I can a better angle on this. We have step stools in the lab. The step stools are, if it's too high up, you can grab a step stool. Let me just show you. And so we have these step stools. So if it's too high up, you know, there's two things you can do. You can remove the burette and then just read it by hand. And so what I do sometimes is I just take the burette off if it's too high up, and then just hold it. You can let gravity hold it, you know, so it's vertical, and then take a reading. You know, obviously you don't want to tilt it in an angle, because then that's going to change the reading. That's one thing. You can remove it, but a lot of people don't like to remove this. This is $200 worth of burette, and it's expensive. And so you can get a little step stool to stand on to aid you if it's too high. This is too low, and so I have to squat down a little bit. So let's take a look. Try to zoom in again. And then figure out what is that reading. Okay, so if we look at that reading, the bottom line there is 22. So this is going to be 21 point. Okay, so we have 21s up here. 21.1, oops, 21.2, 21.5, 21.6, 21.7. This is 21.7. So it's between 21.7 and 21.8. What would you read that as? $21.79. I probably would, because I would think 9 would be a little bit closer to the line, because here's 7. Here's 780, and then right in the middle of these two lines is 785. And so if we're right in the middle, that's 785, then we got to go 786, 787, 789, 790. This would be the 790 line. And so for me, I would read that closer to maybe a 21.78, yeah, you know, or a 7.7 even. You know, 7.7 could be because if the center there, but we're reading it right from the bottom of the meniscus, so, you know, 7.7, 7.8. Okay. The other issue I have is some parallax. If you look at this, this is the 22 mark, and I can see the front of it, and the 22 mark goes all the way around. And so I have some parallax. I'm looking down at it, unfortunately, because I can see the front and the back. If you take a look at this, the 21 mark, I can see the back of it, but the back of it is below. Here, the back of it is above. And so I'm kind of looking down. I have some parallax here, a little bit, and that's going to screw up potentially my measurement here. So we'll see. We'll see how this run goes, and then go from there. And so this is point. Well, let's calculate the volumes here for this particular run. And so it's 20.3, so we've got 19.95 milliliters of sodium hydroxide, subtracting those two. And then we'll subtract these two here. And so actually, I'm going to just use a calculator for that. This is just going to be 2178. 2178 minus 192 was our initial 1986. And so this is going to be 19.86 milliliters here. All right, so let's see what we got here. So I'm going to go ahead and calculate the molarity. And so it's going to be 1986, convert that into liters. And so 0.01986 liters of HCl solution times 0.1032 moles of pure HCl per liter. That's going to give me how many moles of HCl? Well, the moles of HCl is the same as the moles of sodium hydroxide. And so that's also the same as the moles of sodium hydroxide divided by the volume of sodium hydroxide in liters. So that's going to be 0.01995. It's going to give me 0.1027. And so the molarity of the sodium hydroxide is equal to 0.1027 sub 3 molar. Okay, so I want 3 good runs, you know, 3 good runs with decent precision. And so let's take a look at the runs I have so far. I have a 1034, I have a 1035, I have a 1015. Let's see what the other ones were. This is why you need a properly bound notebook. This is not a properly, because this page just tore out. We don't want the notebook pages to tear out easily like this. You're going to lose them. And so this is why I had you guys get a lab notebook with a sewn binding. A sewn binding, the pages aren't going to come out like this so easily and be lost. Then I have a 0.09845 and a 0.1020. And so what we need to do is we need to pick the 3 closest runs. And so the 3 closest runs looks like run 3, run 4, run 5 was a 1015, and then run 6 is a 1027. And so we're going to pick 3, 4, and 6. And so we'll do the percent difference using 3, 4, and 6. And so those 3 runs. And so the biggest was a 1035 1. 1035 1. The smallest is now going to be 1027. 1027.3 divided by the smallest, 1027.3 times 100%. And what's that going to come out to? It's going to come out to 0.10351 minus 0.10273 equals divided by 0.10273 times 100. Okay, this gives us 0.759% difference. Okay, this is unfortunate because this is still greater than 5%. We need a precision that's less than 5%. We're getting closer, but it's still not good enough. Since it's not good enough, we're going to have to do run 7. I think, yeah, normally I might be getting into the record, for students. Some students get it in 3 tries. They get it in 3 tries. They get good precision at less than 0.5%. Other students, like me, are taking a lot of runs to do this. The only danger of that is running out of chemical, but we have enough chemical for this. And so we're going to continue on with it until we meet the criteria, initial, final. And I think the earlier runs, I was suffering from how I shot the, I think I'm still inconsistent with how I shoot the reading, with the camera. I think I'm getting parallax still, unfortunately, but hopefully I'm getting better. Maybe I should just read them by sight first. Okay, so we washed this flask here. I've run out of clean flasks. And so what I'm gonna do is I'm gonna wash another flask here. It doesn't take too long to wash. Actually, I've already had these soaking in soap. Do that. So get the bottle brush.
Professor?
Yeah.
It's break time.
Oh, is it break time? All right. Yeah. Okay, it's 12:30. Yeah, we'll go on a break. Let's go on a break for 15 minutes.
Can you also check the chat, please?
Okay.
Thank you.
Very good. I'll talk about the exam after the break, or after we finish this lab. Let me talk about the exam. I did email. She didn't get my email, Kazra? All right, let me try sending it one more time. Sorry about that. Hopefully it's not too full now. I think okay, we're going to get started again here. So just continue washing the flask here. So you want to just scrub the inside surface and the bottom soapy water. And then we'll rinse with warm, there's no warm water right now, but pretty soon there's just warm water. rid of the residual soap. And then give it a final rinse with DI water. Again, the DI water is just to wash off the tap water. I don't need a tremendous amount. I'll just rinse off the outside too. Okay, that should be good. Okay, we don't have to dry it. We could just use it wet, but I'll just dry the outside so you can tell in case I make any splatters on the outside. This can go in the waste. Our last run. There. Okay, so I'm going to add acid to this. I still have enough. I'm going to use the last reading as my initial. Oops. Well, I'll just do it over here. And so the last reading of the HCl, 19.86. I'm going to do that as my initial reading here, 19.86. Says I'm not going to need more than 20 milliliters. This is 50 milliliter burette. And the last reading for the sodium hydroxide was 19.86 is wrong. I made a mistake. This one is correct, 19.86 milliliter, 2178. And so the last reading for the HCl is 21.78 milliliters and 20.30 milliliters for the sodium hydroxide, 20.30. We want to make the mistakes, again, in the lab notebook, not in the report sheet. All right, so I'm going to add about 20 milliliters of HCl here. And so I'm starting about, what did I say, 21.78. So I need to go to 41.78. And so here, I need to make sure I stop around there. So I'll go ahead and drain this. I'm draining it rapidly, keeping an eye on that. 41, just about. So this is about there. That's a little short, but that's okay. So make sure there are no drops stuck on the tip there. Looks good. Okay, let's move this one out of the way here. So I'm going to raise this a little bit and then just rotate the other one in. I'm going to lower this one. There. Okay, so that was a little short. It was around 20.6 maybe. And so I'm going to drop in about, let's see, I used a little bit more in this run, sodium hydroxide here. And so I'll go about the same, maybe a little less. So we're starting this one at 20.3. So I'm going to go to about 40. I don't want to go to 40. Let's go to about 19.8 roughly. I mean 49.8. 49.8 should do it. Wait, no, that's not right. No, 39.8. 39.8 should do it. 39.8 is going to be still far undershoot. So let's stop here. I want to put in, I forgot the phenolphthalein. I need to put the phenolphthalein in here. 1, 2, do 2 drops of phenolphthalein. So let's go to 39.8, which is about here. So I'll just watch it. I'll just let it flow. You can see the pink color is already developing there. So before 39, maybe 39.3, 39.4 should be good. Okay, that's about 39.2. You can see there's a pink color there, but that pink color should disappear. Let's just make sure I didn't misread anything. So it did disappear. So I'm going to go about 39.4. And so there's 39.4. There's a little bit of pink in there. That should fade as well. Okay, so I'm probably within half a mil, which is 10 drops. So that's close enough. I can go slow now. Just go slow. 10 drops is not going to be too tough to endure. And so that's at 1 drop. Nothing happened to the color. Let's see if I can get a better focus here. Okay, 2 drops, a little bit of color is coming. 3 drops. Okay, now there's some more persistent color. So I'm going to swirl this just to make sure. Oh, this is leaking. You can see that there's a drop developing on the tip. So I'm going to tighten this a little bit. I had loosened it because it was too tight. And it's hard to twist. Loosen a little bit. I have a lot of splatter on the inside walls. So I want to try to wash the splatter in. Now that could be sodium hydroxide or HCl since I had the valve full open. But I got to be very careful because I don't want any liquid to come out. And so the other way of doing splatter is to just squirt the inside walls of the flask, which I'll do because I have a lot of splatter on the neck here. And so I'll probably do that now. And so to get rid of that and to make sure, because that might be drops of sodium hydroxide or it might be drops of HCl, which is going to affect how much of the other stuff I add to it. Okay, there we go. So I've washed that in. So let's add another drop. This could be better washed, actually. I could have scrubbed it out some more. There's still a lot of drops adhering to the inside surfaces. Okay, that was a full drop. Nothing happened there. Let's go with another full drop. Okay, I'm starting to get some color there, but I don't think the color is going to stick around. Here. Let me move this a little bit over this side since I did get some water on the paper towel. Okay, another full drop. It didn't do much to the color. Go with another full drop here. Get the camera right. Okay, I see a little bit of pink. Actually, yeah, a little bit of pink. It's probably not going to persist, so let me go ahead and add another drop. Did I forget to record? No, I did. I got it recording. Okay. Not much has happened to the color. How many drops is that? Like 4 or 5 drops? Okay, a little bit of color. Go with another drop. Okay, a little bit of color. Let me swirl that. I got some pink color there. It's starting to persist. So what I'm going to do is I'm going to go half drop now. So actually, I got a half drop suspended there. So this thing's leaking, unfortunately. Let me tighten it. But when I tighten it, it makes it hard to twist. So I might over twist this. Probably not. Let's try to get a half a drop suspended. That was about a quarter drop there. This is about a half a drop. Okay, a little bit of color, not much color. So let's go for another half a drop. Okay, there's a half a drop. Wash that in. Okay, now I'm seeing a little bit more color. Let's spread some water on that side. but it's hard to see. So we'll go with another half a drop here. Okay, so suspend that and then wash it in. Okay, I can see a little bit more color. I don't think that's going to amount to much. You can see it right in the center, and as it diffuses out, it's probably going to disappear. So let's try another half a drop. Okay, I got the half drop there. Go ahead and wash that in. Okay, now I have a bit more color there. Let's see. That color is not persisting either. And so we'll continue at half drop increments. I want to get the endpoint to a half a drop. Endpoint is, when the color persists at least for 30 seconds. Will be the endpoint of our titration. There's also something called the equivalence point. Endpoint is when there's some kind of indication. The equivalence point is the exact equivalence point of, the stoichiometric equivalence point. Sometimes they don't match, like the endpoint's slightly off from the equivalence point. So that's why we have this distinction between the two. Okay, I definitely have a little bit more color, but it's really pretty hard to see. So repeat. Okay, now I got some color in there. Probably can barely see it. It didn't last. Another half a drop. Push that in. Got some color there. Again, it's not going to last, I think. Let's go for again. Oops. Oh, well, it was a full drop. And not only was that a full drop, I have a quarter drop suspended on the tip, unfortunately. But it looks like it's okay. I have pink color there now. Will persist. Here, let me move this for a second. You guys can see it. Pretty hard to see through the camera. Maybe I'm imagining it. Let me hold this like this. Yeah, there's definitely a pink color to it. Fairly detectable. Let's go with another half a drop, just to make sure, but okay. It's a half a drop. I might be overshooting it because this color is persisting, but you just get a little nicer color to it. Now it's pretty dark. Okay, we're going to go with this. This color is going to persist, I'm pretty sure, because it's dark enough. So let's go with the clock. It's already been 10 seconds. Well, the color is definitely persisting for 30 seconds. Depends on the angle that I hold this at. There you can see a little bit of pink there. Let me swirl this to make sure it doesn't disappear. No. This might be a little bit more than the last run, but it's okay. We'll see what we got. Okay, so that again, this is Chem 1A. Chem 1A, you have to worry about overshooting. We don't want to overshoot the titration for Chem 1A. Oops. Let's take a reading. Actually, I'm going to raise this up. And then take the reading here. I think I might be getting better holding the camera in the right place. Got to blow it up. Might be a little off, but we'll see. Okay, that mark there is 40 milliliters. And the next one is going to be 41. So let me make sure. Yeah, 40. So it's 40 here. And you can see, you know, oops, you probably can't see because I'm not holding it, right? You can see there's a little parallax. You can see I'm looking from above because I see, you know, this is the 40 line here. And so I can see the back of that line. You know, the back of the line curves around. And so it looks like I'm a little too high, the reading is, but I thought I lined it up pretty well with the camera angle. That's parallax. The other lines don't circle all the way back around. So, but anyway, we'll just go with this. Hopefully it's good enough, but what is it? Okay, it's going to be 40.1, 40.2. So it's 40.2 something. And so what would you call that? 40.2. 40.23, 40.25. Well, you have to do, if this is 40.20 and this is 40.30, then 40.25 is dead center. And so if we look at dead center, we're measuring from the very bottom of the meniscus. And so it looks as if it's just past the center. If it's just past the center, I might go with a 40.26 in this particular case. Because I want to measure from the very bottom of the meniscus, which we had colored black. We colored the bottom of the meniscus black with the paper. And so this is actually the bottom meniscus here. And it looks like it's more than midway. And so I'm going to go, let's go with a 40.26. The sodium hydroxide milliliters. All right, let's take a reading for the acid. The acid's in the other burette here. Tighten this clamp so it doesn't fall down. And then again, try to avoid parallax. You know, it's easy to do with your eye because you kind of get at eye level. So you can see it that way. But with this, let's try this now. So you'll probably have more success getting a decent recording, just recording with your eye. But it is handy doing the camera because it really blows it up. But the only problem is where you hold the camera. Like I can hold it in different positions. Like, actually, let's hold it into, let me show you what I mean by different positions. what I mean by different positions is take a look at this. And this is, because I don't usually take a camera to do it, but anyway, this is 41, this is 41.5. So it looks like it's 41.5, maybe 3, 5.2, 5.3. Do you see that? Because 5.5 would be in the center, and then this would be 6.0. So 5.0, 6.0. So 5.5 is in the center, and therefore it looks short of the center. So maybe a 5.3. That's what I call it. That was one picture. And then I took another picture of the very same meniscus. And this is the very same meniscus, but I just held the camera just slightly off, you know. And when I look at this one looks like maybe a 6.0. It's right on the line. And so that's a huge variation to go from a 5.3 to a 6.0. It's the exact same meniscus. And all I did was I moved the camera up or down just like a centimeter or two. You know, it wasn't that much. And so this is leading to poor precision, I think, on my part, because, you know, we're on run 7. And so it's really sensitive to where you hold the camera. And so let me try to make sure I hold it, you know, the lens. I'm trying to aim the lens now so that the lens is perpendicular to the meniscus as best as I can. Because I don't think I was as consistent when I first started. And so this is why the initial results may be way off. Just the way I held the camera, because I was holding it in the center of the phone, and that's going to be way off. So let's see there. So I think that's it. These are things you think about, you know, measurements really, we got to be consistent with measurements. Otherwise, we're going to get very poor results. And so this is where I think the camera lens was perpendicular to the meniscus, where I think it was, but I probably need, you know, a partner or somebody to make sure, you know, because that the lens is actually at the same level. And then when we look at this one looks like it's right in the dead center. You know, the bottom of the meniscus looks right on the 5. So in this particular case, I would do a 41.55. But what did you guys get for this particular one? I just am curious. You got a 5.4, so you're getting it right before the dead center. Okay, let me see. Yeah, 5.4, you could go with that. You know, that works. 5.4. Myself, I would do a 5.5 because I see it right in the center, at least the bottom. Now the bottom is kind of tricky though, because I'm not doing it from the center of the black line on the curve. I'm doing it from the very bottom, because how much of that black line I get depends on where I raise this. I can darken it more or just get the very bottom by moving this up or down. And so, okay, let me just go with a 41.55, you know, but it could easily go with 5.4. You should be consistent, because, you know, as long as you're consistent, then that'll help eliminate precision issues. So you want to read it the same kind of way. So let's just take a look at the sodium hydroxide. Sodium hydroxide is going to be 40.26. Let me do that here. Do a 40.26 minus a 20.3 gives 1996 milliliters. And then the HCl is going to be a 4135 minus a 21.78. No. Oh, shoot. I need to redo that. 41.55 minus a 21.78. 0.78, 1977, and 1977 milliliters here. All right, now let's do the calculation. So I have my milliliters of HCl divided by 1,000. That gives me the liters of HCl solution times 0.1032 moles of pure HCl per liter of solution. This is how many moles of pure HCl times 1 mole of NaOH per 1 mole of HCl. So this is how many moles of NaOH I have. Divided by the liters of NaOH solution. The liters of NaOH solution is 0.019996 liters. So I just converted that into liters. And so I get a 0.1022. 0.1022. And so the molarity of the NaOH is equal to 0.1022 molar, 1022.1. Now for day 2, this is day 2. So for day 2, we have decent precision here. We got a 1027 and a 1022. Okay, but we need 3 runs with decent precision. So let's pick the 3 closest runs. And so 1027, 1022, a 1034, a 1035, 1027, 1022. So, well, and a 1015 here. Let's see what else we got. And then a 1020 here. And so I'm going to pick the 1020 sub 7. That's run 2. And then go with run 6 and 7. And so we'll calculate the percent difference. And so it's going to be for runs 2, 6, and 7. And so the smallest is going to be a 1020 sub 7 here. That's going to be run 2, 1020 sub 7. And the biggest will be a 1027. And so it's going to be a 1027 sub 3 minus the smallest, which was a 1020 sub 7, divided by the smallest, which is a 1020 sub 7 times 100%. And so let's see what this gives us. So a 1027.3 minus a 1020 sub 7 equals, divided by 1020 sub 7 times 100%. Oh, bummer. This gives us a 0.646% difference, which is still greater than 5%. And so what that means is this is probably getting into record category, but we need to do run 7, or I need to do run 7. And so let's just set that up here. So I'm going through so many flasks here. We'll just clean these. So this one I'm going to dump in the waste here. And so let's actually this is a pretty decent flask, so I'm just going to reuse this one. I'll put a little bit of soap in here. This is still pretty dilute. The HCl and the sodium hydroxide is pretty dilute. And so I'm Not too worried. Otherwise, I'd wear gloves. Anyway, it's a good idea, a good practice to wear gloves and lab. Two rinses would probably be adequate. Just rinsing off the tap water here with the DI. Just dry the outside. Okay, now I'm going to have to refill these. And so let me get my base. Put that in here. And the acid. Sure. Need to lower this. This is the acid standard solution using the funnel. If you leave the funnel sealed here, it doesn't drain. You're going to overfill it. It doesn't drain very well. Catches. So we need a little air gap there. All right, I overshot both of them, so I'm going to dump a little bit into the waste jug, the waste beaker here. And so I overfilled both. So let's bring this below the 0. And let's bring this one below the 0. Okay. Okay, take a reading. I'll take the acid reading here. Okay, let's hope, oops, came out with blurries. Can hold it steady. Try one more time. All right, so this is the 0.5 mark right there. And so there's 0.6, 0.7. It's between 0.7 and 0.8. And so what do you call that there? 0.79? Yeah, or 0.78. Yeah, actually either 0.78 or 0.79, you know, because 0.80 would be right in the center of that black. And so, you know, either of those are good. Let's see which one we'll go with. Let's just go with a 0.79. It's almost touching that line. So let's say HCl initial 0.79 or 0.78. Again, consistency, that is, you should read this for both initial and the final. If you had your partner, if you're doing this with a partner, then you should switch off. Take both readings on them. Switch off. Let's see. It looks like about the right height. To get it focused. Not focused. One more time. Let's see if I got that. Okay. Looking at this one, it looks like, okay, so we got 0, 0.1, 0.2, 0.3. It's between 0.3 and 0.4. So what would you call that? Okay, 0.35? Yeah, 0.35, that looks pretty good. Let's just go with that, 0.35 milliliters. It looks like it's pretty much right in the center. All right, so now I'm going to get the flask I just cleaned. Let's dump this one in the waste here. So raise this burette here, move it over. Okay, then lower it. So the HCl was about 0.8, so I'm going to go to about 20.8. So I'll just let it drain rapidly until it gets to about 20.8. Oops. It's about there. So I have 20.8 mils roughly. Take a more precise reading later. Let's go with the sodium hydroxide burette. So I'm going to rotate this over. We have clamps. There's a little wing nut here used to loosen it or tighten it. Yeah. And then I'm going to lower this a little bit to prevent splatters. We don't want it to splatter on the outside. Okay, and then let's watch this here. And so I'm starting about 0.3. What was it? Yeah, 0.3. So I'm going to go to about 19.9. Let's go to about 19.9. And so let's make sure I don't overshoot it. So 19.9 is about here. So I'll just let it drain rapidly until it gets to about 19.9. Okay, that's roughly there. Okay, then let's do, hopefully this one goes well. We'll see. So again, I'm not sure if that's DI water, you know, residual, or if that's from splattering happen. And so probably it's a good idea to wash it in with the wash bottle, just in case it was splattering acid or base. We want to make sure everything reacts. I'll also swirl it in. Okay, rotate this. Let me raise it so it's easier to see the drops. Okay, so I need to add some phenolphthalein. I don't think I added the phenolphthalein yet. I'll just add 2 drops. 1, 2. And I'm going to add just a drop. Oh, that was 2 drops. But I know I'm at least, maybe 10 drops away. Anyways, so 2 drops is not, or shouldn't do anything. Okay, let's add another drop. I tightened this, so it's hard to twist. I might loosen it. Okay, for a full drop. Let's see, no color, so I'm going to add another full drop. Okay, there's no color there, so add another full drop. Still no color. A little bit of color, but not enough. Okay, another full drop. Now I'm seeing a little bit of color in the center. I just want to swirl it to make sure that things are mixed. Okay, I'm going to go with another full drop here. No color. Let's go with another one. Okay, no color. Another one. Still no color. Okay, another one. Now we're getting a little bit more color. Swirl that. Another one. Not much is happening, so that was 2. Not much. Okay, a little bit more color right in the center, but I'm going to add another drop. Okay, a little bit more color in the center, but let's swirl this and see. Okay, the color dissipated. Now I'm getting close. And so I probably want to go half drop now. Let's try to suspend. There's already like a quarter drop suspended on there. Make it a little bit bigger. It's about half drop. Probably need to make this a little bit lower. Wash that in there. Okay, not much has happened. It's just a moment. Okay, so we get a half a drop suspended on there. Wash that in. Nothing. Okay, there was already half a drop of water, so that was like a half a drop. Okay, half drop. I'm going to squirt it in. I see some pink color on the side. That tells me there's some splattered base there, so I need to swirl this a little bit better. Okay, there's still some pink color there, so I didn't wash all the base droplets in there that got splattered on the side. let's make sure we're in there. You know, if we're going half a drop, it goes slow, obviously. The titration goes slow. So we go half a drop when we get close. But if I underestimated it, then it's going to take a lot more time. But what happens is people begin to lose patience, and then they add a whole bunch in and overshoot it. So. Or they start running out of time. Which can easily happen. I might have stopped with one drop interval a little bit too early, but it looks like I'm starting to get close now. So. Wish that was a full drop. I definitely have some pink color there. But it didn't last. Okay, again, color's starting to persist a little bit longer, so I'm getting close. Got another half a drop. Another half a drop. Okay, I can see some color there. But it disappeared, faded. Another half a drop. Let me lower this a little bit because I don't want it to splatter out. I'm gonna lower this. I'm gonna make sure. So you can see a little bit more pink color to it. Okay, but it looks like it faded out. Oops, that was a full drop. That was more than I wanted to add. Okay, there is pink color there. Let's see if it stays. 30 seconds. That's probably it. Well, I didn't set the timer. I can still see the color. But we're right on the cusp. And so maybe I'll just overshoot it a little bit. I'm just going to do another, I'll just do another half a drop. I might have went with this. Okay, we'll just go with this now. I'm going to set the timer. For stopwatch. All right, that was more than 30 seconds here. And the color is still there, but really hard to see. Really quite hard to see. And so we might go with this, or we might add another quarter drop. Again, because I had that a little bit darker color on the last run. So maybe they'll do that. This color is also really hard to see, but let's see. It lasts for 30 seconds. But this is a little bit darker than the last one. Okay. I still see the color there. Maybe on the black background it might be easier to see. Let's try that. It's pretty hard to see. Well, anyway, let's go ahead and take some readings here. It might be, it depends, the paper, it looks like the paper is impinging a little bit of color to this solution as well. All right, so I'll take some measurements here. Raise this up a little bit. Let's go with this. All right, so this is the base. Okay, what do you read for this? Well, actually, this is the 20 here. So this is 20.1, 20.2. So it's between 20.2 and 20.3. And so maybe It does look like a 7, you know, but yeah, like a 20.26 or 20.27. You know. Could even be an, well, no, probably not an 8, but 20.26 or 20.27. I'd probably go with 27, yeah. Let's do that, 20.27 milliliters as the final base. Okay, let's get the initial acid. The pink color is still there, although I'm worried that the paper is making it look a little bit pink. Let me see. No, I guess not. Okay, let's get the acid. Tapped it a little bit, but maybe it's all right. Okay, what do you record that as? There's a 20 line up there. Well, you have to think, you know, right in the center here between this line and this line would be 20.5. And so it looks like it's closer to the mid mark than it is to the initial. And so 20.52 is, you know, I'd say it's pretty close to a 20.5, but maybe slightly above it. So maybe like a 20.54. You see that? And so let's go with a 20.54. It could, yeah, it could be even a 5.5. You know, when we look at the bottom, the very bottom of the meniscus, could be right in the center. But we'll just go. Let's go with a 5.4, 20.54 milliliters. All right, that's our reading. Now, I want to show you something here. We want to be consistent. The easiest and the most consistent place is to go from colorless to colored. And so we need to get that, just a light pink color in there. That's it. But what happens if we overshoot with too much? If we add too much base, then we're going to get a deeper color, you know. But it's hard to judge it by the shade of pink that we have. You know, if we're trying to titrate this to some shade of pink, sometimes it's very difficult. And so let me just show you what I mean by that here. And so there's just a very, very light pink color there. But let's add, I'm going to add, let's see. That's another drop, another drop. I'm just dripping it in there right now. Let's see what happens to the shade of pink. Okay, I'm going to stop there. If I stop there, take a look at the pink color here. Very light. So you get a light pink color. Okay, I'm going to keep adding it drop by drop. As I add drop, it's still dropping. So it's going drop, 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 drop. That's the drop rate there. But take a look at how much the color changes. It doesn't change that much, you know. And so it's very hard to titrate it to a certain shade of pink. So this is about 20 drops now. That's like a milliliter past where we stopped or more. Okay, then I'm gonna just go ahead and pour it in. I'm gonna dump it in there like this, and then take a look. If I dump in a whole bunch in there, yeah, it's gonna get a little bit darker. Darker, but it's hard to titrate it to a shade of pink. Here. So that's what we did. But it was kind of hard to titrate it to where the color changed because it was kind of hard to see, you know, that color change. It's so faint. But I think we got it. And so let's go ahead and calculate the volumes here, and hopefully we'll be done with this. We just need it within 0.5% precision. So. Okay, so it would be 8. This would be 19.98 milliliters. 25. This should be 19.75 milliliters. Okay, so let's do the calculation now. So I'm going to have 0.01975 liters times 0.1032 moles per liter. So moles of HCl, which is the same as moles of sodium hydroxide, divided by 0.01998 liters of sodium hydroxide solution. And so I got a 1020 this time. 1020. And so the molarity for run 7 for sodium hydroxide came out to 0.1021 molar. So let's pick the 3 closest. The 3 closest are going to be 1020, 1022, and a 1027. And so that's going to be runs 2, 7. Oh, this is 7. This is 8. 8 runs. Wow. This is going to be runs 2, 7, and 8. I think. Let me just make sure. Fortunately, my notebook is falling apart. The pages mixed up. I need to renumber the pages in order. Okay, so that looks right. Percent difference between 2, 7, and 8. And so the biggest of these 3 is 1022. Here, 1022.1. The smallest will be a 1021 divided by the smallest. Ideally, we should be getting better and better, but I don't know. It's hard to tell, so sometimes it's best just to take all your data and not eliminate. And normally in science, we don't eliminate any data like I'm doing right now. I'm eliminating all the other runs. I'm just picking 2, 7, and 8. But we don't know about random error. You know, random error, you know, maybe it wasn't, these aren't the 3 best. Maybe the 3 best were actually others if I kept doing this more and more. That's all part of the statistics. The reason we're doing it this way is because you're learning how to titrate. And since you're learning how to titrate, we want to make sure we're getting consistent readings. My readings weren't so consistent. And so maybe because I was trying to read them off the phone instead of reading them off the burette with my eye. Normally I get pretty consistent readings, but and so for me, this would be kind of a similar type of situation. If you aren't used to using a burette, then, you know, if you aren't used to using a burette, then it's going to be tough initially. And so you just keep going and get more practice. Well, I think we finally did it. I finally did it at a 0.196. And so I got about 0.2%. Well, 0.2% is less than 5%, 0.5%. And so we're good. And so we're going to pick 2, 7, and 8 as our consistent runs. All right, now what we're going to do is we're going to get the average molarity, but we're going to throw out all the other runs. And so we're only going to pick the 3 closest for the average. This is the average based on the 3 closest, the 3 runs. And so the run 8 had a 1020 sub 1. Run 7 had a 1022 sub 1. And run 2 had a 1020 sub 7. Okay, divided by 3. And so we'll just average those 3 runs. So a 0.1020 sub 1 plus a 0.1022 sub 1 plus a 0.1020 sub 7, and then divided by 3 gives me my average molarity here, 1020 sub 9, 0, 10, 20 sub 9 molar. And then we're only allowed 4 sig figs, so I'm going to round this to 1021 molar sodium hydroxide. So what we did here is a process called standardization. We standardize the sodium hydroxide solution. That is, standardization means determining its composition to a high degree of precision and accuracy. So this is our high degree with 4 sig figs is what we got it. So you got a 1021 molar sodium hydroxide. And so this is the end of part 1. All right, so I guess it's, Kazra didn't remind me, it's break time now. So we're gonna take a break, but this break is going to be a little bit longer. I have to run to the post office really quick. Yeah, that's right. So I'm gonna go to the post office and then I'll be back. And so it will be at least, it depends, hopefully there's not much of a line there, but we'll take a little bit of an extended break right now, okay? Like 20 minutes at least. All right, I'll see you guys back then. I'm going to stop the recording, pause the recording. Well, one way to make up some points is to turn in if you're missing any quizzes, to turn them in or fix them. If I asked you to fix a quiz or something, fix it. But we are going to have one other thing. We're going to have this thing for nomenclature. You know, since some people, it wasn't clear for some about the charges. So we're going to have a nomenclature quiz before, or probably during the final exam plus nomenclature. Now, the nomenclature, I'm not sure how I'm going to do that just yet. whether it's going to be take home or on Canvas. Yeah, I need to, yeah, I'm going to do those, Natasha, soon. Start inputting them today. I got to finish grading your exam too as well. I'm quite done with that. Okay, so we're going to skip exam 3. I need to actually I need to lecture a little bit today as well, but then this experiment 13 is just more demo lab. Just do some reactions, redox reactions. Experiment 12, there are a lot of reactions here. So the first thing I want to do is I want to cover experiment 12. On the final, you're going to have some reactions that you'll have to figure. And so let me take a look. Oops. Some of those. So let's take a look at experiment 12. All right, so we're going to skip exam 3.
Thank you, Professor.
Yeah, thanks. No problem. That actually helps because I got to catch up. And so we'll skip exam 3. We're going to have a nomenclature thing. Yeah, and the nomenclature will be some bonus, so some people can make up, but everybody will have opportunity to get some points from this. It'll be a mini exam. I have to figure out how many points it's going to be. All right, I need to move on to lab 12 here. Let's see. Let's follow on. Okay, now I have the right PDF up here. So let me take a look. The numbering. Okay, I have, again, sorry, I had the numbering system, the numbering all mixed up because I didn't have a copy of this until right before. It's experiment 11. Experiment 11 deals with qualitative analysis, and so that's what we're looking at for right now. So let's take a look through the lab first. All right, qualitative analysis is just to try to figure out what's present. So let's say if you have some tap water. Now we know tap water has certain things in it, like salts and minerals, that kind of stuff. And so qualitative analysis is just trying to figure out what's present, you know, what minerals or what salts or what ions are present. There's something called quantitative analysis. Quantitative analysis tries to figure out not only what's in it, but how much is in there. And so qualitative analysis is just, is there sodium in that water, or, sodium ions or not? That's qualitative. Quantitative would be, is there sodium in that water, and how much, if there is? Now, there's something with detection. Different tests have different detection sensitivities. This is the whole thing about that. Dr. Michael Mina from Harvard, he's having trouble with that particular test because FDA has a certain sensitivity requirement for the test. So for example, if you want FDA approval for your COVID-19 test, then it has to meet a certain detection reliability limit, and that could be like 95%. So it detects 95%, and maybe 5% it tests negative when they were actually positive. And so, however, the test that it depends. Compared to the PCR, it's all relative to the PCR, but the PCR is overly sensitive because the PCR is catching too many, people who aren't infectious, people who have gotten over the virus. And those people are testing positive, but they're already past being sick with corona. And not only that, they're not infectious, so they can't spread it to others. And this has been documented in studies of family members, of people who tested positive, but nobody came down with coronavirus, even with close proximity to those that tested positive. Here, for qualitative analysis, we want a highly sensitive test, but some tests are so sensitive that they cause trouble with contamination. So, for example, when I was at UCLA, I was working on analyzing sodium. Well, the problem with sodium analysis is, in your perspiration, you have sodium ions. Sodium ions are very ubiquitous. They're everywhere. So everything you touch, you leave sodium ions. And so the possibility for cross-contamination is extremely high. It's so high that, a lot of glasses contain sodium ions as well. And so I didn't bother using any glass, in my analysis, because sodium ions could be leached from the glass, contaminating my sample and giving me a false positive because the test was so sensitive. And so I ended up using polyethylene. There shouldn't be any sodium ions in polyethylene plastic, or minerals or salts or that. But in a lot of glasses, depending on the formulation of the glass, there could easily be leachable sodium ions in the glass. And so that was a lot of work, to try to prevent contamination of my samples by sodium ions present in nature. And so I couldn't touch anything. I couldn't use glass. I use polyethylene, everything, polyethylene beakers, polyethylene flasks, polyethylene, everything, vials, and no glass. Well, we want a highly sensitive test. The more sensitive tests, the better, because, we want to detect even minute quantities of it. But some of these tests aren't that sensitive. For example, the test for lead. And so what that means is if you get a negative test, it doesn't mean you don't have lead. It just means the test wasn't sensitive enough to detect it if you had it, or maybe you don't have it, and so it depends. Like the lead analysis isn't so sensitive. So you could have it and still test negative. And it's just because the concentration is either below the detection limit, or maybe it's zero, you didn't have it. And so negative is inconclusive, but a positive is fairly certain. If you get a positive test, then that means that you had it present, like a false positive. So false positives do happen, like when people contaminate, cross-contaminate, when people misinterpret the analysis. But, false positive is kind of rare, because if you get a positive, it's a positive. You have the species, as long as methodology is sound, but a negative is ambiguous. You know, a negative means it may or may not be there. And so let's take a look at the qualitative analysis experiment. The objective is to gain experience in observing some identifying chemical reactions for selected cations and anions in known aqueous solution, to relate observations of chemical reactions directly to net ionic equations, to apply qualitative analytical procedures in the identification of selected cations and anions. So we can just skim through this. The use of systematic procedures for the identification of species present in a given sample of materials termed qualitative analysis. In part one of the experiment, you will be introduced to chemical methods for the separation and identification of selected ions in aqueous solution. Solutions of known composition will be studied so that you'll become familiar with the chemical reactions and properties of the ions tested. An understanding of the purpose of each step in the procedure and the logical sequence of each step is essential to successfully fulfilling the objectives of the experiment. And so, yeah, we want to understand the chemistry that underlies these tests. That way we can better interpret the results and observations that we get with this. The competence and proficiency gained from this experience will prepare you to carry out similar analysis with solutions of unknown composition. This will be the objective part 2 of the experiment. And so in part 1, we're going to run all the tests on a sample that we know, contains all the species. And the sample contains all the species. We should get positive test results for every single species. Now, what are the species? We're going to test for ammonium, silver, lead-2, barium, and manganese cations. And anions, we're going to test for chloride, sulfate, and nitrate. So we're just going to try to detect the presence. If we get a positive test, then that indicates that we have these ions present. If we get a negative test, we may have it. It's just below the detection limit, or we may not have it. Okay. And so we're going to have some chemical reactions with this. And it's going to be a mix of different types of reactions here. So let's take a look at some of the reactions here. These are the reactions. And it goes through a discussion, long discussion of the reactions we observe here. And so you read through this. Let's see. Some of these are individual standalone tests. Some of these are part of a sequence of steps and the sequence of tests that have to be done in this particular order. So here's the procedure. So the first part was just talking about the reactions. And this is just a cookbook. The cookbook, you don't really think about what's happening. You just mix the stuff together. Okay. These are the standalone individual tests. And so, for example, if we're going to test for ammonium, we take 3 milliliters of the sample. It's going to be the cation/anion mixture. So let's say ammonium, silver, lead-2, barium, manganese-2 ions are present, and we add sodium hydroxide. What's going to happen is the sodium hydroxide will react with ammonium. And so ammonium is an acid, and hydroxide will pluck that hydrogen off ammonium to create ammonia. Now, ammonia is a gas, and so eventually it'll evaporate off, and you can smell it. And what it is it's a gas that's also a base. And bases turn litmus blue. And so if we take some red litmus, it'll turn it blue. But how do you test a gas? I'll show you how to test a gas. It's different than testing a liquid. Okay, but sodium hydroxide not only reacts with ammonium, it reacts with other species as well, because hydroxide, like silver hydroxide, is insoluble. And so let's take a look at some of the reactions here in this particular test. Well, we'll do that. Blow this So the first reaction is with the ammonium, and let's look at the tests here. So basically, if we have ammonium in here, and the ammonium is going to be in solution, and the sodium ions are going to be a spectator. And so what we're doing is we're going to add hydroxide ions here. Basically, the sodium is not going to do anything. And when the ammonium and the hydroxide react, we form ammonia. So ammonium aqueous plus hydroxide aqueous. That's going to form, well, it's going to form ammonia. The ammonia is going to be aqueous, but you know, it's also a gas. And so some of it will come off the surface as a gas plus H2O liquid. And so what we're going to have down here after this reaction is taking place is we're going to have ammonia aqueous down here. And some of that ammonia aqueous will go into the gas phase. So we'll have a little bit of ammonia gas. We can detect the odor. Ammonium has no odor. Ammonia does have an odor. And so it'll just smell like ammonia cleaner. But we don't have to smell this because, you know, ammonia doesn't have a very pleasant odor. And so the way we're going to test the gas is like this. We're going to get a watch glass here. Show you what a watch glass. I'm surprised I don't have a watch glass. Watch glass is just going to be a beaker, and then we're going to stick a wet piece of red litmus underneath the watch glass. And so we'll just have a watch glass as like a cover. Here. And the wet litmus will stick to the bottom of the watch glass. And so we'll put a piece of red litmus on the bottom of the watch glass. Wet, red, litmus. And what that's going to do is it's going to turn, gradually it's going to turn blue because what's going to happen is the gas, it's 2 ammonia gas here. Ammonia gas is going to rise off the surface here. It's got to be the gas. We don't want the liquid. If the liquid splashes up, then it'll turn it. But we want the ammonia gas to come up and gradually change the color of the red litmus here. And so the reaction for that is going to be like this. It's going to be ammonia gas plus red litmus Okay, red litmus is actually a acid, and so we'll call it HLIT. Litmus has a formula, but it's a very long formula because it's quite a big acid. And so this is red litmus, which is a weak acid. Okay, and the ammonia is going to pluck the hydrogen off the litmus. And so what we're going to end up with is ammonium ion and LIT minus. LIT minus is blue. And so this is the acid. The acid and the conjugate base is just its base that it turns into, are different colors. And so we can see. And so this is a detection for ammonia gas, but the only way we're going to get ammonia gas is if we had ammonium present initially, because ammonium present initially will react with the hydroxide to create that ammonia gas. That's a test. Now, there are some interfering reactions or side reactions that are occurring here. And so let's take a look at the side reactions. Silver ions also like hydroxide. You know, this is metathesis. And it should form silver hydroxide, AgOH. Ag is a plus, and OH minus is a minus. And so let's go with 2. We're going to take 2 silver ions and 2 hydroxides to make 2 silver hydroxides. This is a solid. But the silver hydroxide is a little bit unstable. Actually, it's quite a lot unstable. And what happens is it decomposes into silver oxide, which is solid, and water, still liquid. And so it turns out this is more stable. This is a acid-base or Lewis acid-base type reaction here. And so we get a black precipitate or dark brown precipitate here if there's silver ion present. Okay, if there's no silver ion present, then we get no dark brown precipitate. There's no precipitate here with ammonium. If we do get a dark brown precipitate, we might also have a white precipitate. Dark brown precipitate will hide a white precipitate, so you don't see it. Lead ions also like hydroxides. So if I had lead 2 ions, they like 2 hydroxides for every lead, and that's going to make a white precipitate, a PbOH2 solid. So this is the white precipitate here. If we have a white precipitate but no dark brown precipitate, then it's likely we don't have silver ions, but we do have lead. These are just little things, you know, that can help you identify. But we have separate tests. We have a separate test for silver ions, and we have a separate test for lead 2, you know. And so the purpose of this test is not to detect silver ions, and it's not to detect lead. The purpose of this test is to detect ammonium. And so it's very specific for that. Here it's not as specific because it's hard, if we get a mixture of precipitates, to tell which one is which. Now, manganese also will form a precipitate with hydroxide. And so if we have manganese here present and we add hydroxide to it, then 2 hydroxides will combine with the manganese. These are metathesis, you know, favorable ion combinations. And manganese likes to precipitate with hydroxide. And it forms a brown precipitate. So if we get a brown precipitate, how do you know which one it is? Is it silver or is it manganese? You know, well, one's dark brown, but you know, shade is very difficult to tell. And so these ones are just side reactions that might give you a little additional clues as to what might be present in solution. So if we're getting precipitates, then it tells us there's something else present in this. And depending on the color of the precipitate, we might be able to infer, you know, what else might be present here. And so this one is a standalone test. So we take 3 milliliters of sample and test it for ammonium. And if we get the gas turning this piece of red litmus that's stuck on the bottom of a watch glass, if that gradually turns blue, due to reaction with the gas, ammonia is a base, then and it's a gas, and then we have a positive for ammonium. And so this is positive for ammonium. Yeah. However, these ones will be inconclusive usually, unless it's white or something like that. Probably inconclusive, other than we have something else present. Yeah, so that's a cation ammonium. Then there's a separate test for the anion, you know. So for example, if we have chloride, sulfate, and nitrate, and we add silver ions, then we only get a precipitate of silver chloride. We should get silver sulfate too, however, it's not concentrated enough. And so this is the test for chloride. The test for chloride is just to add some silver. And so what we're going to get is silver ions like chloride ions, metathesis. And we're going to form a precipitate. This is the driving force for the metathesis. And this is a white precipitate. silver chloride. However, when we have silver ions and sulfate ions, we'll need 2 silver ions. We end up getting NR, no reaction, at these concentrations that we use. And if we have silver ions and nitrate ions, we end up getting no reaction. Nitrates are all soluble. Sulfates are all soluble except for silver, lead, mercury, etc. And so sulfates are all soluble except for silver. Silver should not be soluble, but under these conditions, silver is borderline. Borderline. So I'll put a little asterisk there. And so under these conditions, it doesn't precipitate. And we get no reaction here. There's no driving force for silver nitrate. No precipitate. And so the test is, if we suspect we have chloride, we just add some silver ions in the form of silver nitrate. Nitrate's a spectator here, so it's not going to do anything. We just get the silver ions and the chloride ions to react to form silver chloride and white PPT. So do that one as well. Okay, the next test is going to be for nitrate. Nitrate doesn't precipitate with anything. And so we're going to have to take advantage of redox reaction for nitrate analysis. And so the redox reaction is like this. We put this in a test tube. And so there's some nitrate present in this solution. If there's nitrate present in this solution, then we're going to add some FeSO4 to this, which is green solution. This is aqueous. So we'll add this FeSO4 aqueous to this, about the same amount. Go down here. And then we're going to add some concentrated sulfuric acid. This is concentrate. Concentrated sulfuric acid is very dangerous. Concentrated sulfuric acid can cause severe burns. Causes severe burns. Second degree, third degree level burns. You have to be very careful. You don't want to spill any of this on your skin. It'll make it like a charcoal. You can see. Let me just show you a little video of what happens when you mix concentrated sulfuric acid with sugar. You may have seen this already.
Build custom industrial machines in days.
I don't know if this
What's
is the
up,
right
everybody?
one.
Welcome back to my laboratory, where safety is number one priority. Safety shield as well, and I got gloves over there, fire extinguisher, on fire, just in case. And in this experiment, we're gonna do a crazy chemical reaction. Let's check it out. For this experiment, we're going to need sulfuric acid and sugar. I got powder sugar, but I don't think it matters what kind of sugar. And couple of tubes, Let's get to it. First, we're gonna put powder sugar. Then we're going to put sulfuric acid. See, the reaction already started. So what we're gonna do is mix it up. I think it got so hot that it was even fun, but how crazy is that? So we're going to try this again, but on a bigger level. So we're going to put sulfuric acid in there, and then we have to mix up sugar.
Basically, it smells like burnt sugar. Depends on how badly. He should have used some more sugar. You can make very, very tall towers. So it's just charcoal.
Really crazy. What do you guys gonna say in comments? What this looks like?
Okay, so that. So you got to watch out, you know, with concentrated sulfuric acid, severe burn hazard. Also, silver nitrate stains everything black, and so this, as well as being a heavy metal, and so there's some chemical hazards here, splash hazards, eye hazards, that kind of stuff. And so what's happening here? Well, what's happening here is iron 2. Iron 2 is kind of interesting. Let's take a look at this redox mixture. Here. Make sure it's all right. So what we have here is we got some nitrate. You know, nitrate's what we're testing for. And then we added some iron 2 sulfate. So there's going to be iron 2 ions, there's going to be sulfate ions. And so when we think about it, well, we have two oxidizers. Nitrate's an oxidizer, sulfate's an oxidizer. Iron 2 can go either way. It's an oxidizer and a reducer. And then we're adding concentrated sulfuric acid. So concentrated sulfuric acid is going to have a lot of H plus and sulfate and HSO4 minus. And so these are the species, you know, that we have. I don't write in necessarily HSO4 minus. This would be concentrated sulfuric acid. It's going to give us H plus and HSO4 minus. But as far as redox properties go, sulfate and HSO4 minus are going to have the same redox properties because, you know, they're both sulfur in the +6.
Professor, it's supposed to be C.
Now, you would think sulfur in the +6 would be a stronger oxidizer than nitrogen in the +5, but it turns out nitrogen in the +5 is much stronger. Sulfur is a much bigger atom. And so this turns out to be, you know, the strongest oxidizer. But we need some H plus here.
Sorry, Professor, for interrupting, but we can't see nothing. We just see a
Oh, you
black.
can't see it? Okay. Let's see. I wonder why that's not. Thought it. Can you see it now?
No.
How about now?
Okay, yes.
Okay. Just had to switch back and forth, I think. All right, thanks for letting me know. All right, so nitrate we know is an oxidizer, so this is an oxidizing agent when coupled with H plus here. You know, it's like, we know nitrates are very dangerous. For example, in China, they had, I think it was potassium nitrate or lithium nitrate. You know, well, if you have something like potassium, let's say you had sodium nitrate, you know, sodium nitrate, we don't really worry about that too much, you know, sodium nitrate. Nitrates, yeah, it's a strong oxidizer, but nitrate really needs H plus, you know, some acid there to help it react, you know. And anyway, it can't oxidize sodium ions. Sodium ions are already oxidized. And so sodium, so this is, yes, this is an oxidizer, but we don't worry too much about it, you know. But if you store this next to some kind of fuel source, like in China, they stored, I think it was potassium nitrate next to, did they store? I forgot what it was. Let's see. Well, I guess it was 800 tons of ammonium nitrate. Wow, that's less than, you know, Beirut was what, 2,700 tons of ammonium nitrate. Well, that Beirut explosion had an incredible shock wave. pretty impressive. Although this did too, but you couldn't see it because. So ammonium nitrate. Oh, I thought it was something else in addition to it. So, sodium nitrate, yeah. Here it is. It stored sodium nitrate, potassium nitrate. Sodium nitrate and potassium nitrate, we wouldn't worry about it because there's no fuel. There's only oxidizer. We need both fuel and oxidizer. Well, here's fuel, carbides. Carbides are fuel, you know. This is carbon in -4 oxidation state. So if you have calcium carbide, it's a very good fuel. Because calcium carbide would have the formula, well, Ca. Is this writing? I guess I can't write on that. Okay, it's not letting me write there. But anyway, it's here. You can see it. CaCa2 with carbon in the. Is that carbide? That's not carbide. Carbide would be carbon in the -4 oxidation state. But nonetheless, this would be a pretty good fuel because it would be carbon in the -1 oxidation state here. So, calcium acetylide would be better. Yeah, that sounds better for the name. Well, there's your fuel. So you have fuel, and you know the carbon's electron rich in calcium carbide or calcium acetylide, and the nitrates are electron poor. But you need a little bit of acid and you need a little bit of moisture to get it to detonate in that way. So where was I? So here, it's kind of important that the H plus is there. Otherwise, if the H plus isn't here, then its ranking drops. Like for example, nitric acid. Nitric acid, I worry a lot more. You know, nitric acid is a lot more dangerous than sodium nitrate or potassium nitrate. That's because we have the H plus there. When we have the H plus there, we're going to form water, which is a fairly stable product. And that's going to help drive the reaction more. And so nitric acid is more dangerous than sodium nitrate and potassium nitrate as an oxidizer. But something like ammonium nitrate's more dangerous, you know, than all of these because ammonium is a fuel. And so we have a fuel and oxidizer in the same compound. You know, it's not the greatest. Ammonium is not the greatest fuel. Like, you know, if you tried to burn ammonium salts, you know, they don't burn so easily. So if you mix ammonium nitrate with an even better fuel, then that's a very dangerous. That's like Oklahoma City, you know, where they mix fuel oil with ammonium nitrate to create that huge explosion that destroyed the federal building there. But here, sulfates is also a good oxidizer, but not as good as nitrate, and so. We see that on the ranking chart, and we need H plus for that. And so this is an oxidizer as well. Then we have iron 2. Iron 2 is both an oxidizing agent and a reducing. So it could go either way. It could oxidize something to go to iron metal, or it could reduce something to go to iron 3. HSO4 minus and SO4 minus is the same, essentially. Same redox. You know, predict. Although this has some acid here, and so that's helpful in this sense for this. And so if this didn't have any H plus on it, then plus. So, but they're roughly the same. Not exactly, just roughly the same. I have to be careful if you know, what I say as far as the same or what's wrong with my screen here. It's not working. Okay, and then there's water. Water is the final thing here. And H2O liquid is both an oxidizer and a reducer. And so when we pick the strongest oxidizer, looking at the chart, is going to be nitrate, and the strongest reducer is going to be iron 2+. And so basically, the nitrate's going to oxidize iron 2 to iron 3. So nitrate and H+ will oxidize the iron from iron 2 to iron 3. Now there's going to be a color change because iron 3 and iron 2. Iron 2 is green, iron 3 is yellow. This is more of a green color, this is more of a yellow color. But we aren't going to use that color change to indicate the presence of nitrate because, you know, sulfate could potentially do the same thing. Sulfate could oxidize it. What we're going to do is we're going to try to detect the presence. Now, when nitrate reacts, we look at the chart, it also forms NO gas. This is not balanced. If we wanted to balance this, then I'd probably just look up nitrate. You know, nitrate plus 4H plus 3 electrons goes to NO gas plus 2H2O liquid. This is from the chart. And then iron 2+, goes to iron 3+ plus an electron. And so we'd need 3 iron 2s, 3 iron 3s, and 3 electrons here. Then we can cancel out the electrons. And so add these two reactions up. 4H+ there. Then now it's balanced. Okay, what we're going to do is we're going to detect the presence of NO. But if you recall, nitric oxide is a CCG. CCG is a clear colorless gas. There's something interesting that happens though, you know, and that is iron 2, this is green in aqueous, in water. But when iron 2 reacts with NO gas, it turns brown. And it's an unusual compound. It's FeNO 2+. This is a strange species, but you have to realize, like, iron 2 occurs in blood as hemoglobin, and so iron 2 can pick up, you know, gases like O2 gas. It can also pick up NO gas as well. So there's probably some kind of interaction here between iron 2 and NO. The body's pretty complex, you know, and so and the body's pretty sensitive to certain changes. So there was something that I saw recently, I'll probably talk about in just a minute, but here, this is an ion here, and this is aqueous. And so this is what we call the brown ring. The brown ring. The brown ring is going to happen like this. So here we're going to have the mixture of iron 2. We need excess iron 2, nitrate, and H+. To this, we're going to add our concentrated sulfuric acid. The concentrated sulfuric acid is like syrup. And the concentrated sulfuric acid, as long as you don't mix it, it's going to sink to the bottom. It's very viscous. It has very strong intermolecular attractions. This will be the concentrated sulfuric acid. It's dense and it sinks. You have to watch out. Lots of heat is generated. You know, like in the sugar, when you mix the acid with the sugar, lots of heat is generated. Pretty much turn the sugar to charcoal. Here. Okay, at the interface here, you know, H+, we need, actually, there's not enough H+ here. There's not enough H+ in our original mixture because we're just taking the nitrate, the Fe2 plus, and the sulfate. And then we're adding the H2SO4. And so as we add the H2SO4, the H plus is all down here. And so we're going to have H plus here. And now with nitrate and H plus together, it's going to make a powerful oxidizing combination. Nitrate and H plus together make a powerful oxidizing combination. And so that powerful oxidizing combination is going to happen right at the interface between the concentrated sulfuric acid and the green iron 2 solution. And so the concentrated sulfuric acid is a CCS, clear colorless solution. The iron 2 solution is going to be a CGS, a clear green solution. So we could call this a CGS, clear green solution. There. And so right at the interface here, we're going to get reaction. And we're going to end up right here is we're going to get something that looks like a little layer of smog. It's going to be like a little smog layer. Smog is NO2. So this is not really smog, but it's going to be a brown layer here. A brown liquid layer as the reaction takes place right at the interface. So if we get a brown liquid layer, we call that the brown ring. And if we get a brown ring, then that means we get a positive test for nitrate. So we had nitrate present here. All right, so that's the nitrate test. Here. Let's look at the sulfate test. The sulfate test is fairly straightforward. It's just metathesis, precipitation. And so when we test for sulfate, sulfate and barium like each other. And so if I have barium ions and sulfate ions, these two ions like each other and will precipitate. They'll precipitate barium sulfate here, solid. Barium sulfate's a white precipitate. And so if we get a white precipitate here, then it's a positive for sulfate. But, you know, in the previous reaction here, we were adding sulfate in the form of FeSO4, and we were adding sulfate in the form of H2SO4. So that means if there's lead present, we'll get a white precipitate, PbSO4. If there's barium present, we get a white precipitate, BaSO4. But the sulfate's coming from the two chemicals we're adding, iron 2 and sulfuric acid. If we get a white precipitate, that's Ag2SO4. And so we could get some side reactions going on here in addition to our dark brown ring right here. And so we'll do 4 separate tests, a test for ammonium on one sample, and then we'll take another sample of our mixture and test for chloride, and then another sample of mixture, test for sulfate, nitrate, so it's nitrate, and then another sample to test for sulfate over here. All right, any questions so far? Yes. Clear that. All right, but for the remaining ions, we're going to test those in a sequence of steps. And the sequence of steps is really well thought out and designed, you know. So what we're going to do is we're going to take a larger portion. This is going to be 12 milliliters. And then we're going to test for these 4 species. And the way we test for it is people have figured out reactions and physical processes to separate and identify these 4. And so separation becomes extremely important here, how to separate. And so the first step here is we're going to separate out the silver from the rest of the ions. Well, how can we do that? Well, we need something that reacts selectively with silver and not the rest of the ions. And so what that species is going to be is chloride. You know, and so we're going to give it some HCl. The H plus is a spectator. In this case, it's the chloride. HCl has multiple properties. You know, when we think about HCl and when we think about chemical properties in general. So let me talk about the properties of HCl over here. Normally when you ask somebody, you know, what is HCl? Well, people will say HCl is a strong acid, which is correct. It is a strong acid, but it has other properties in addition to being a strong acid. So yes, it's a strong acid, and that's what stands out most about HCl. But other properties are it's a moderate oxidizer. Why is it a moderate oxidizer? It's a moderate oxidizer because of H plus. You know, this acid H plus can oxidize many metals like zinc, aluminum, etc. H plus is a decent oxidizer, not nearly as strong as nitric acid because nitrate is a much more powerful oxidizer, but it's still a pretty decent oxidizer. It's a weak reducer. H plus is a weak reducer because of chloride. Chloride is, you know, chloride could lose an electron. So if you have a powerful oxidizer, say like hydrogen peroxide, you mix hydrogen peroxide with hydrochloric acid, you're going to get chlorine gas, you know, because hydrogen peroxide is going to pluck electrons from chloride and make chlorine. And then chlorines are going to pair up to form a diatomic molecule, and we'll end up with green, yellow chlorine gas. But we don't need hydrogen peroxide. We could use potassium permanganate. In fact, this is a chlorine generator. And one of the demo reactions I showed you on YouTube, this is how they generated chlorine gas. You know, you could buy it in a cylinder, or you could make it yourself. You make it yourself by adding or mixing hydrochloric acid with potassium permanganate. That'll generate chlorine. And then you can use the chlorine to react with things like sodium metal. I think that was the reaction we saw. There's one more property of HCl, and that is it's a precipitating agent, you know, in metathesis. You know, because of chloride, metathesis, chloride. Chloride likes silver ions, chloride likes lead ions, lead 2, and chloride likes mercury 1. Chloride likes these 3 ions, and it will form a precipitate. So in this first step, what we're going to do is we're going to get chloride and silver to react with one another to form silver chloride. But at the same time we form silver chloride, we also have lead 2 ions in there. And lead 2 ions like chloride ions as well, and should form a white precipitate lead 2 chloride solid. And so both of these will precipitate. However, barium and manganese will not precipitate. Those ones will not precipitate. Now, the thing is, we don't want a mixture of white precipitates. Both of these are white precipitates. What we want is we only want the silver chloride. Well, it turns out that's not so difficult to do because of the solubility in hot water. The solubility of silver chloride in hot water is minimal, barely any dissolves. But in hot water, lead 2 chloride, a significant amount dissolves. And so this is quite soluble in hot water. In hot water. Whereas silver chloride is not very soluble in hot water. And so this is why we're going to heat it. We're going to heat it. The heating part is going to dissolve the lead 2 chloride. And so we'll end up with lead 2 chloride aqueous here. Whereas if we heat this one in water, heat it in water, we get essentially a minuscule amount will dissolve, but not significant enough to lose it. Whereas here, when we heat this in the presence of water, this dissolves, all of it should dissolve. And so by heating it, then that'll redissolve this and will form lead 2 ions and chloride ions. And so we redissolve this. And when we have a soluble salt, it breaks up into ions. And so lead ions, barium ions, and manganese ions end up here in solution. Whereas the silver ions are trapped in the lattice, the silver chloride, like PPT. But how do we know we dissolved all the lead, you know? How we know is we'll do one extra step. This is called the confirmation test. And the one extra step here is this. What we're going to do is we're going to add sodium hydroxide to the white PPT. Now, if we didn't dissolve all of it, this is what happens. If we didn't dissolve all of it, then there will be lead-2 hydroxide solid here. And so what's going to happen is if we add sodium hydroxide to lead-2 hydroxide, we get no color change. Or the precipitate might dissolve. We have multiple choices depending on how much sodium hydroxide we have. 1, it appears that there's no reaction. 2, the white PPT dissolves. White PPT dissolves. And 3, if there's no lead in there, what happens when we add sodium hydroxide is it converts the white PPT into a black PPT. That is, when we have silver chloride here, and we add the sodium hydroxide here, we'll have to do 2 silver chlorides and 2 sodium hydroxides. What happens is we'll have an ionic exchange. This is a solid to solid change. And so it's going to go to 2 silver hydroxides plus 2 chlorides. Now the silver hydroxide is unstable, and that's going to decompose into silver oxide, which is the black, plus water. And so converting silver chloride into silver oxide, this is a positive for the presence of silver ion in our original sample. Here. All right, so it's a break time. So we're going to take a break right now. I'm going to, yeah, let's take about a 15-minute break. I'll be back. I'm going to pause the recording. Or actually, I'll stop the recording right now.